Okay, to finish today up, what we're going to be working on is some stuff with polynomials. So we're going to want to remind ourselves what polynomials are. And then the main thing we're going to focus on is using synthetic division along with polynomials in order to factor. So polynomial is a function that can be written in the form we'd say an x to the n plus an minus 1 x to the n minus 1 plus so forth and so on plus a2x squared plus a1x plus a0. an minus 1, all of these coefficients. For our class, we're going to say, we're not going to look really at polynomials too much that have complex number coefficients. So for our class, we're going to say these mostly should be just decimals. They could be positive or negative. These n values here, n minus 1, so we'll say n, that needs to be a natural number. So we want it to be a positive whole number. Or I guess we could say it could be 0. So you could have like just a constant number is a polynomial also. So say n is that, or 0. So we get a couple terms here. This whole initial bit here is called the leading term. This last bit here that doesn't have an x attached to it is called the constant term. The power n here, this is called the degree of the polynomial. And this a subscript n, this is the coefficient of the leading term. We call that the leading coefficient. So polynomials, basically, they look like numbers times x to whole number powers. So if I wrote something like this, say f of x equal 2.4 x to the 7th minus 3.61 x to the 5th plus x to the 4th minus 2x squared plus x minus 3. My leading term, this would be the term with x to the highest power in it. That would be 2.4 x to the 7th. My constant term, that would be the negative 3 without an x. This is a polynomial because all the powers of x are positive whole numbers. The numbers in front of the x's are just, the real numbers are just decimals, and there's no negative powers, no fractional powers. So this is going to be a polynomial, and all these individual terms are all added or subtracted together. So we got leading term, we got our constant term, leading coefficient. That would be the 2.4. And the degree of this is a degree 7 polynomial because in this standard form, 7 is the highest power that you see x raised to. So that's what a polynomial is. Again, you can't have fractional powers. The powers have to all be positive whole numbers. You can't have any negative whole numbers there or fractions or any of that sort of stuff. What we're going to look at is kind of, first of all, reminding ourselves how does synthetic division work. Then we're going to look at doing synthetic division to factor a couple polynomials and kind of talk through the process for a couple of examples there. And then that'll wrap it up for the day. So what we're going to look is, let's say we had a polynomial, f of x equaled, let's say, 3x to the 4th. Plus 4x cubed minus 2x plus 5. And we want to divide that by x minus 3. So first of all, let's say using synthetic division. So first of all, you can only apply synthetic division when you're dividing by x minus a number or x plus a number. If this is like dividing by x squared plus 3, we can't use really synthetic division. It's, x cubed plus x squared minus 2x or something like that. Can't use synthetic division to divide. Only works when the divisors of this form. So what you're going to do, you're going to draw a symbol like this. You put the leading coefficient first, and then you start counting down powers and using the coefficients of the lower powers. You use 0 for any missing power. So leading power is x, it's degree 4. The leading term is 3x to the 4th. You use the leading coefficient 3 first. 4 is x cubed's number. There is no x squared, so we use 0 for our placeholder. Negative 2 is x's number. And positive 5 is the constant term. And what we do is we got x minus 3. So whenever the x minus 3 is out to the side and you go to do synthetic division with it, you're going to switch the sign on the value that you're subtracting. So in this case, instead of negative 3 going out here, we put a positive 3 out there. So we're trying to divide the positive 3 here indicates we're dividing by x minus 3. So we're going to use a little pattern here. What we do is we bring the first 3 down. So that first 3 here drops down. 3 times 3 makes a 9. 4 plus 9 makes a 13. 3 times 13 is a 39. 0 plus 39 is still 39. We got to do a 39 times 3, which, let's see, that's 3 times 3 is 9, 10, 11, so it's 117. We take 2 away from that, so we get 115. We're going to multiply that by 3 again. That'll be 5 carry the 1, 3 plus 1 is 4, then 3, so we get 345. And we add 5 to it, so we get 350. Now, in this case, this is the remainder. So that's remainder. These are the coefficients of the quotient. You start counting, this is no x's number. This will be x to the first power's number. This will be x squared's number. This will be x cubed's number, and you just keep counting up by powers of x till you run out of numbers. So we're out of numbers at x cubed. So we're going to write this out as the division algorithm says it goes. So this division is equal to, it's the quotient of the division plus the remainder over the divisor of the division, and that would be our synthetic division. So let's maybe do one more of these synthetic division types just to make sure that we feel like we got the hang of it. So I'll write one here. Let's say we want to do this next example. Suppose we want to do 3x cubed minus 2x squared minus 150, and we're trying to divide that by x minus 4. So to get started on it, we're going to try to perform this division. We're going to put the positive 4 out to the side there. We put 3 for x squared's number. We put 3 for x cubed's number, negative 2 for x squared's. We're missing the x to the first power, then negative 150 out here for the constant term. So if you guys pause the video, try to go through and do this, do the little pattern here, see if you can get your quotient and your remainder out. So pause the video there, give that a shot, and I'll work it through here in just a second. So what we're going to do is we're going to bring the 3 down. 4 times 3 makes a 12. Negative 2 plus 12 is a 10. 4 times a 10 makes a 40. 0 plus 40 is still a 40. 4 times 40 is 160. Negative 150 plus 160 ends up being 10. That's our remainder. These will be the quotient terms, so that's no x power. This is x to the first power. This is x squared. So our answer will be 3x squared plus 10x plus 40. So that's the quotient plus the remainder, which is 10, over the divisor. If there's a 4 there, we were dividing by x minus 4, and that'll be our synthetic division. Okay, so what we're going to look at next is a couple problems that are, these are types where we use synthetic division to factor. We're going to use, in these previous ones here, we used the form of the division algorithm that was dividend over divisor equaled, well, here we got quotient plus remainder over divisor. If we took this whole equation and we multiplied it by a divisor, you could get a second form of the division algorithm, which is dividend equals divisor times quotient plus remainder. And this right here, this form, is what we're going to use whenever we try to factor stuff using synthetic division. So it's the second form of the division algorithm when we try to use synthetic division to factor. So what we're going to do here is we're just going to work out a couple quick problems. And this is going to use the rational zeros theorem and stuff, which we're not going to write the full theorem out. I just kind of want you to show you guys the process you would go through to do this, and then when we get to this in the course, we'll write the full theorem out and everything there. So we're going to say f of x equals x cubed plus 5x squared plus 2x minus 8. And we want to factor this completely. So we'll note that factor by grouping is not going to work. So unless you guys do the synthetic division trick with rational zeros theorem, you're gonna have trouble getting this to factor. So what we're gonna do is we're gonna get two numbers, p and q. P will be the last number out here without the x. It'll be the constant term, -8 in this case. Q will be the leading coefficient, so that's the number in front of x cubed's term in this case, which there's nothing written there, which means that's a 1. We're going to label all factors of p and all factors of q. So all the numbers that divide evenly into -8 are plus minus 1, plus minus 2, plus minus 4, and plus minus 8 itself. All the numbers that divide evenly into 1 are just plus or minus 1. So we're going to take every combination of these p-values here and divide them all by plus or minus 1 and make a list of all combinations that can occur. So 1 over 1 is 1, 2 over 1 is 2, 4 over 1 is 4, and 8 over 1 just happens to be 8. So we have a list here of positive 1, negative 1, positive 2, negative 2, positive 4, negative 4, positive 8, negative 8. These are possible rational zeros. So these are possible rational zeros. So these might be zeros of this polynomial. We're not 100% if they are or they aren't. Since this is a degree 3 polynomial, at most only 3 of these 8 zeros could work. So some of these definitely aren't zeros. So what we're going to do is we're going to do synthetic division on this polynomial, starting with the easy numbers first, like positive 1, then negative 1, then positive 2, and negative 2. And we're going to keep going until we find one that has remainder 0. So I'm going to set up with synthetic division. Our coefficients here are 1, 5, 2, negative 8. So 1, 5, 2, negative 8. And we're going to start on our list with positive 1. So we're going to see, does positive 1 work? So we're going to do synthetic division. Again, what we want is out here, we want remainder 0. So I bring down 1. 1 times 1 is 1. 5 plus 1 is 6. 1 times 6 is 6. 2 plus 6 is 8. 1 times 8 is 8. Negative 8 plus positive 8 is 0. So we got really lucky, and the first number we tried, positive 1, happened to work and gave us division by 0. So we were told to factor this completely. So what we're going to do now is use that form of the division algorithm, which says divisor, so our dividend f of x equals divisor times quotient plus remainder. So if we have a 1 here, that tells me the divisor is actually x minus 1. These numbers here tell me information about the quotient. This is no x number, that's x to the first power, that's x squared. So our quotient is x squared plus 6x plus 8. Plus our remainder is 0. Plus 0 doesn't do anything, so we don't have to put a 0 here. So what's happened is our original function f of x that we didn't know much about, we currently have it broken up into a degree 1 times a degree 2 polynomial. And you all know a lot of information about how to factor a degree 2 polynomial. So to factor this thing completely, we can factor x squared plus 6x plus 8. We've got this thing fully factored. So I need to think, what are two numbers that multiply to 8, add up to 6? That would be 4 and 2. And we have our function fully factored. So our goal was to completely factor the function. As a side note, it didn't ask us this, but once you get it fully factored, it's easy to get the zeros. So this is just kind of like a little side note. X minus 1 creates the 0 at x equals 1. X plus 4 would create a 0 at x equals negative 4. And x plus 2 would create a 0 at x equals negative 2. So these right here, these are the zeros of the function f. So we fully factored it. It only asked us to factor, so we didn't need to find the zeros. But once you factor it, you can extract the zeros from the factored form pretty easily. All right, so we're gonna look at one more of these synthetic division types, and then we'll probably pause on stuff there. So next example, we're gonna say f of x equals x to the 4th plus 2x cubed minus 7x squared minus 20x minus 12. This time we want to find all zeros. So this is really, if we're wanting to find all zeros, we're going to factor it first. So one thing we should note, this previous one was degree 3. We ended up with 3 factors, and each of those 3 factors produced 3 zeros. This is degree 4, so we're going to end up with 4 factors, and each of the 4 factors should produce 0, so we'll end up with 4 zeros. So in this case, we'll say, all right, p is negative 12, that's the constant term. Q is going to be 1 again, that's the leading coefficient, and since there's nothing in front of x to the 4th, that happens to be 1. So we'll get plus or minus all the numbers that go into 12, or negative 12. So that'd be 1, 2, 3, 4, 6, and 12 itself. And all the stuff that divides into 1 is just 1. So if we look at all combinations of these over 1, our list of possible rational zeros is just, whoops, 5's not 1, is just that list that we have there. So this right here is list of possible rational zeros. Okay, so we're going to start with this list, and we're going to start going through and doing synthetic division on our polynomial. So 1 is x to the 4th's number, 2 is x cubed's number, negative 7 is x squared's number, negative 20 is x to the first power's number, and negative 12 is our constant term. We want remainder 0, so I'm going to start out with the easiest to work with number. I'm going to put a 1 there and see if we get remainder 0 from the 1. So I bring down 1. 1 times 1 is 1. We get a 3. We get a 3. We get a negative 4. We get a negative 4. It's a negative 24. It's negative 24. Negative 12 plus negative 24 is not going to add up to 0. So that one doesn't work. So we're going to reset, and we're going to move on to negative 1, because that's kind of the next easiest one to do. So I'm resetting my number. Instead of using positive 1, I'm going to use negative 1. So we get 1. That's going to be negative 1. That'll be negative, just kidding. 2 take away 1 is 1. Negative 1 times 1 is negative 1. This will go to negative 8. That'll make a positive 8. Negative 20 plus 8 is negative 12. Negative 1 times negative 12 is positive 12. And here is a 0. So what this says, if I had a negative 1 there, I have x plus 1. So my original function is x plus 1. This is no x's. This is x to the first power. This is x squared. This is x cubed. So it's x plus 1 times x cubed plus x squared minus 8x minus 12. So I still don't really know how to factor a degree 3 polynomial like this. It's not the same as like the degree 2 polynomial when we had to factor x squared plus 6x plus 8. This one's harder. So what we're going to do is we're going to continue on in our list and say, okay, well, we got negative 1 worked on the original one. So positive 1 didn't work, negative 1 did work. We're going to continue on in our list, but instead of using the original numbers, we're going to set up with the coefficients from this, the output, which is the quotient from the previous division. So I use 1 for x cubed, 1 for x squared, negative 8 for x, and negative 12 for the constant. So instead of using the degree 4 polynomial stuff, we said the degree 4 polynomial factored up as a degree 1 times this degree 3, which means the rest of the zeros have to be in this degree 3 polynomial. The one that we found is kind of taken care of by this factor, so the rest of our list here, all these other possible zeros, if they are a 0 and there is another one that works, it's got to be in here somewhere. So we're going to continue on and say, all right, we use negative 1, let's look at positive 2, then negative 2, and we're just going to kind of keep looking with these numbers. So we bring down 1, 2 times 1 is 2, that adds up to 3, 2 times 3 is 6, that's a negative 2, 2 times negative 2 is negative 4, so that doesn't get us a 0. So we'll reset with our new degree 3 numbers, 1, 1, negative 8, negative 12. We'll reset and we'll try negative 2. So we bring down 1. Negative 2 times 1 is negative 2. That adds up to negative 1. Negative 2 times negative 1 is a positive 2. That gives me a negative 6. Negative 2 times negative 6 is positive 12. That gives me nothing, so I found a second one that worked. The second one that worked was negative 2. So our function f of x equals, we still got this x plus 1 factor out front. But now from the degree 3 polynomial that we had hanging out here, this degree 3 polynomial, we're splitting it up as the negative 2, so that's going to be x plus 2. This will be no x, this will be x to the first power, that'll be x squared. So it'll be times x squared minus x minus 6. So it's divisor times quotient plus remainder. The remainder is 0, so we don't need to write it. That's why 0 is the one that we're looking for when we do these divisions, is if there's like a plus 7 out here, then the thing doesn't factor perfectly and stuff gets messed up. But if the remainder is 0, then the factorization goes through nice. And now we can use our regular old tricks that we know about how to degree 2 polynomials factor, and we can factor this part down the way that we normally do. So I need two numbers that multiply together to be negative 6 and add up to be negative 1. So it's going to be negative 3 and positive 2. So we have 4 factors from this. The positive 2 turns up twice. So we could say our function f of x is x plus 1, x plus 2 squared times x minus 3. This is the fully factored form. We're supposed to find the zeros. So each factor creates a 0. X plus 1 creates the 0 at x equals negative 1. So that's 1, 0. Since the factor that creates the 0 at x equals negative 2, which is the x plus 2 factor, since that factor turns up twice, we say that that x equals negative 2 has multiplicity 2. So I'm just going to say it's negative 2, and I'm just going to put for multiplicity 2 beside it, just to note that there were 2 factors that create the 0 at negative 2. And then x minus 3, that's 0 when x is positive 3. So we'll say, all right, well, x equals positive 3. That is our last 0. And so we're asked to find all zeros. We found there's, I guess, 4 of them as long as you count the negative 2 twice. There were 4 factors for a degree 4 polynomial. Each of those 4 factors created a 0. We had negative 1, negative 2, 3, and negative 2 again. So here's all 4 of our zeros. Negative 1, negative 2 gets counted twice, and positive 3. So we'll stop on synthetic division and polynomial stuff. We'll stop there. And that'll be kind of it for reviews for the day. Thank you.